So last time we were together, we talked about the idea of what's called a rational number. And a rational number is, if you remember the definition, it's at the very top of the notes sheet from that section. A rational number it's basically a fraction, it's division of two integers, and the decimal representation of a rational number always either terminates, like the fraction 1/2 is 0.5, done, or it repeats, like the fraction 1/3 is 0.33333 forever and ever. So then that begs the question, okay, if there's rational numbers, if that's the case, what's the opposite? What's an irrational number? That's what we're going to talk about just a little bit today. We can't get in too much depth just because of our of the math knowledge we already have, but we're gonna look at one example that probably you're sort of familiar with. So an irrational number basically is a number you can't write as a fraction. Okay, so irrational numbers cannot be written as a fraction. And so what that means is that the set of irrational numbers, I'm just reading here this sentence, the set of irrational numbers is the set of numbers that cannot be written in the form a over b, which is just what I said. They can't be written as a fraction. Said another way, because I know we like decimals better than fractions, irrational numbers cannot be written as a decimal that repeats or terminates. So what that means is irrational numbers, their decimals are decimals that never repeat and they never end. Okay, they are, I'm sure they're not random mathematically, but they are seemingly random. One of the most famous irrational numbers is pi. Pi is defined as the ratio of the circumference to the diameter of a circle. We talked about pi just a little bit when we were dealing with the circumference and the area of a circle, and we can use an approximation that terminates, but in reality, pi never ends. And if there's websites that have pi wallpaper where you can print out millions of digits of pi if you're feeling nerdy and you want to put it all over your wall. And you can look through, and there is never a time where pi begins to repeat and have a pattern. Another common irrational number results from square roots. And this is where we're going to focus our attention. There's a lot of famous irrational numbers, but again, our mathematical knowledge, we are not getting into the algebra of things to talk about a number like e or a number like psi, things like that are also fun. Another fun one is the golden ratio, which there's all sorts of fun stuff. Maybe I'll talk a little bit about that in our last section when we talk about what's called sequences. Anyway, all that is to say is we're just gonna look a little bit at irrational numbers that come from square roots. So before we do that, just in case it's been a while for you, first question is, what is a square root? Okay, great. Well, a square root is something written like this. I've got this check mark looking thing that is an operator symbol. What this symbol right here is called, that check mark, that is called a radical. And what it is telling you to do in the case of what's written right there is it is telling you to find a number that multiplied by itself gives you the number under the radical. Now, math people love to have words for everything, and so the number under the radical is called the radicand. Now, we're just doing a super brief survey of this. If you've had like an intermediate algebra class, then you've seen this. We're only going to deal with square roots, so I don't have a number in the basket here of the check mark. Some countries do put a number there for square roots. They might put a 2. If there is a number here in the basket, that is called the index. Now, while it's not part of the knowledge I need you to have for this class, the index tells you how many times you multiply a number together. So in our case, we're dealing with square roots. The index would be 2, but in the US and some other countries, because it's the most commonly used radical, you don't put the 2, it's just assumed. But if there was like a 3 there, that'd be what's called a cube root, and what you'd be looking for is a number 3 times that gives you the number under the radical. Okay, so we're only concerned about an index of 2, but I was just letting you know. So here we go. We're going to evaluate this. I hope this is a fairly relaxed question, but what number times itself gives you 36. 6. Yep. Perfect. Now that's called the principal square root. We're not going to worry about about -6 times -6 is 36. We're just dealing with the principal square roots. So just real quick, exercise 1, exercise 2 right below it. Go ahead and evaluate those two problems for me, please. So what is the first one? What's the square root of 81 going to give me? 9. 9 times 9 is 81. Notice, please, because this is probably the most common mistake. I don't think I've ever had a student that doesn't know that, but what students will do is maybe put a radical over the 9. But here's the thing, the radical is an operation symbol like a plus or a minus. Once you've done the operation, the symbol goes away. So you don't need the radical anymore. So it's not radical 9 that is the answer. It is just plain old 9. All right, how about the square root of 25? The square root of 25 is perfect. 5 times 5 gives you 25. Perfection. So far, we so good. Anybody got any questions, comments, or concerns for me? Okay. Well, you might be thinking, well, here's my question, Perkster. You told me we were going to talk about irrational numbers, but all those numbers are rational numbers. So 6 is just 6 over 1, and 9 is 9 over 1. 5 is 5 over 1. So far, you haven't shown me what square roots have to do with irrational numbers. Great question. So to answer that question, an irrational number is the result of taking the square root of a number that is not a perfect square. 36 and 81 and 25 are numbers that are called perfect squares. They are the same number times itself. So the perfect squares would be the name of my band if I had any sort of musical talent, but I don't. I sing for volume. That's all I got. So it's good to be behind me in church or in front of me. You want to be behind me in church, not in front of me. Anyway, all that's neither here nor there. So some examples of the perfect squares are just these. I'm listing these because they're going to be relevant to your future using these. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5, 25, and then we got 36, and then 49, and 64, and this is just very relaxing. 81, 100. I'm just going to go a couple more. 11 times 11 is 121, 12 times 12 is 144. We could keep going on and on and on, but I'm going to leave my list there. Those are perfect squares. Those are numbers that can be written as the same number times itself. So, for instance, something like the square root of 2. 2 is not a perfect square. If you go to your calculator will give you an approximation of the square root of 2. For instance, my calculator tells me that the square root of 2 is equal to, let's see, we got our square root symbol right here. The square root of 2 is approximately 1.41421352. And then I don't know if that 2 has been rounded or not, so I'm not going to read it off. But notice so far, there's been no repetition. It doesn't terminate except that the calculator screen ends. That's the limitation here. But if we have the ability to derive the process, which there is a process to come up with the exact value, we would keep writing forever and ever the digits of the square root of 2 because it is an irrational number. Okay, so what I want to do then is what happens if I have a square root that I want to leave exact and but I do want to simplify it a little bit. So this is kind of where we're driving our discussion of square roots and irrational numbers is dealing with roots. And again, you might be saying, hey, why do we do this? Well, like I said before, a lot of you are going to take statistics. You will encounter a lot of square roots. That's why I picked the focus on this particular topic. I want this class to be relevant to what you're going to do in the future. So what we're just going to do is practice playing around with square roots and simplifying them. So hopefully it's a skill that when you need it, if you do take statistics, you'll be able to use it. So for instance, the square root of 24. 24 is not any particular whole number times itself. It is 6 times 4 or 8 times 3. Students always point that out to me, but 8 and 3 are not the same number. Okay, so that doesn't help me as far as taking my square root. So here's what you're going to do when you're asked to simplify. A radical. Also, it's not the produce rule for roots; it's the product. So spell check did not help me there because I did spell produce properly. Okay, but it was just not the proper word. So what we're going to look at is what's called the product rule for roots, or the product rule for radicals. So square root of 24. Here's the question you're going to ask yourself, and I'm going to write this down so that you remembered it. Remember it. Does 24 have a factor that is a perfect square? I can't write the square root of 24 as just a whole number answer. So what we're going to do is kind of like a fraction. We're going to try to reduce this to something. So I wrote down a little list of perfect squares. Is there a number on that list that divides evenly into 24? I'm gonna spoil the surprise. Yes, there is a number on that list that divides evenly into 24. What is it? 4. Yes, 4 goes into 24 exactly 6 times. Don't be shy with your calculator. I mean, I let you use calculators in here, and so the relevance is we're simplifying a radical. Your calculator is not going to tell you what the simplified. It'll give you a decimal approximation, but it won't keep it exact. So you can use your calculator here. So 24 is 4 times 6. Again, why did we pick 4 times 6 instead of 8 times 3 or 12 times 2? We picked 4 times 6 because 4 is a perfect square. Now here's where what's called the product rule of radicals, or the product rule of roots, comes into effect. What the product rule of roots says is what I can do, since I have a product under here, is I can give each of 4 and 6 their own house, their own radical. So I can separate this into the square root of 4 times the square root of 6. So I've changed nothing, except I've given each of them their own radical. And the reason I want to do that is now because I used 4 times 6, what's the square root of 4? 2. So I'm going to write a 2 with no radical. Okay, that is the answer because we have done the operation. Square root of 6, since it has no perfect square factors, that's an irrational number. That's a number that I can approximate, but if I write it down, I can't write it down exactly because it's a decimal that never repeats and never terminates. So I'm going to leave that as square root of 6. Notice this 2 is not in the basket. It's not a degree. It's a coefficient. So it's full size. Okay, so I've got 2 times the square root of 6. And we're done. We have simplified that. It is now a whole number, 2 times an irrational number, square root of 6, and we're good to go. Seem reasonable? We're going to practice that process a couple times. All right, so the next one, exercise 3 right below. You're going to do the same thing. First thing you're going to do is you're going to figure out what is the perfect square factor of 45. There is one. There's no tricks or gimmicks here. And then you are going to simplify the square root of 45. Just to give everybody a nudge, what is the perfect square that divides evenly into 45? What'd you say? 25 does not divide into 45. 25 times 2 is 50, so that's going to be bigger than 9. Yeah, okay, so 45 is 9 times 5. So give you another minute or so in case you were stuck there or didn't quite get it. It's all good. So 9 times 5, 9 goes into 45. When I use my calculator, 45 divided by 9 is 5. And so what I've got is I'm going to use the product rule of radicals or the product rule of roots to give them each their own operator symbol. And now square root of 9, what is that? When I evaluate it, it's 3. No more radical for the 3. It is done because I did the operation. Then the square root of 5, it no longer has any perfect square factors. That's an irrational number. Okay, so to write it exactly, I'm going to leave it square root of 5. Again, the 3 is not an index. It's not in the basket. It is a full-size coefficient. If you got a question, ask it. If not, move on to exercise 4. Yeah. Okay, so the question, in case you didn't hear it, is she wrote it as square root of 5 times 3, like that. Okay, so I'm going to advise against it for a pair of reasons. Firstly, you don't want to accidentally be communicating the wrong thing by extending the radical bar too far. Okay, so math people will write the whole number coefficient first, just as a matter of clarity. So it's not wrong per se, but you just got to be real careful. I'm a messy writer, so I would never write it like this because now it looks like the square root of 53. Okay, so great question. I appreciate that. And on the test, as long as you're clear that it's the square root of 5 times 3, I won't mark it wrong at all. All right, exercise 4, square root of 300, please. All right, what's the perfect square factor of 300? Okay, so I heard that we're going to use 100 times 3. Now, I'm guessing that somebody in here might have done something a little different, and I want to address it. So 300, you can also divide, because 100 has other perfect square factors. So you might have said something to the effect of 300 is, let's say, 25 times 12. Or maybe you said it was 4 times 75. Okay, I'm going to show you how to address that. You're not wrong. Okay, so that's not a wrong first step. So don't erase it. I'm going to show you what to do. So 100 times 3 is the direct. It's the one-step answer. So 100 times 3 is, I'm now going to give them each their own operator symbol, their own radical. And then the square root of 100 is what? 10. 10 times 10 is 100. And then I've got the square root of 3. Now, you might be saying, okay, great, I see that, Perkster, but I had picked 25 times 12, or I picked 4 times 75. What would I do in that instance? And that is a great question. Here's what you have to do. So when I give them each their own house, I've got the square root of 25. That's my first. And then the square root of 12. Now, here's what we notice. Does 12 have a factor that's a perfect square? So in each of the other examples, 100 times 3, 3 doesn't have any additional factors. When we did 9 times 5, 5 doesn't have any additional perfect square factors. 4 times 6, 6 does not have any additional perfect square factors. But down here, if you picked 25 times 12, here's what you notice. 12 can be written as 4 times 3. So this is just the two-step way. There's nothing wrong with it. Okay, sometimes you got to break numbers down into smaller numbers. So don't beat yourself up. Don't erase it. Just go with it. It's perfect. And now we'll do the product rule of radicals again. And that's the square root of 25 times the square root of 4 times the square root of 3. The square root of 25, we've already done this example. Square root of 25 is 5. Square root of 4, I think we did that earlier. That is 2. And then since both of these numbers are both outside the radical now, 5 times 2 becomes 10, square root of 3, which is the same thing I got. We don't get a different answer. Okay, we just went about it a different way. Okay, nothing wrong with that. Questions, comments, or concerns before I turn the page? All right, so what we're going to do on the next page is the product rule of roots, or the product rule of radicals, can be done in reverse. So what I mean by that is now I've got the square root of 6 times the square root of 15. Since they're both under a square root, what I can do is I can combine this into one root, the square root of, and then you just go to your calculator and you're going to say 6 times 15. So that's great. I can do that. My calculator loves to do that. 6 times 15 is 90. And at this point, if possible, it's not always going to be possible, but if possible, at this point, you say, okay, does 90 have a factor on my perfect square list? And pretty clearly, what's a factor of 90? 10 is, and it's 10 times what? 9. There you go. There's what I'm looking for. Okay, 9 is on the perfect square list. It's 3 times 3, so 9 times 10. Product rule of roots, or the product rule of radicals, says I can now give them each their own operator symbol. And when I do that, the square root of 9 is 3. 3 times 3 gives me 9. And then the square root of 10, that is an irrational number. And so I'm going to leave it as the square root of 10. That's as simple as I can write the square root of 10. All right, so exercise 5 right below it is a little bit of a simpler version. Simple doesn't mean easy, but it's a little bit of a simpler version of what I just did. So multiply and simplify square root of 7 times square root of 7. All right, when I apply the product rule of roots, or the product rule of radicals, square root of 7 times the square root of 7, when I combine it, becomes the square root of what? Yep, 7 times 7 gives me 49, and 49 happens to be a number on my perfect square list. What is the square root of 49? It becomes 7 without the radical. Okay, we've done the operation. No more radical is needed right there. So we've got square root of 7. We doing okay? All right, the next problem, exercise 6, is more like my example. You're going to multiply those two things like we just did, but then you will be able to simplify the result. Okay, so I'm going to apply the product rule of roots, the product rule of radicals. So when I multiply these, I get the square root of what? What's the first step? 20. Yes, fantastic. If you did that, you're halfway to the finish line of this problem. Great. And now 20. Does 20 have a factor on the perfect square list? Yep, it's 4 times 5. Wonderful. Now the product rule again, so we're using the product rule twice, says I can now give these each their own operator symbol. And so the square root of 4, what times what gives me 4? 2, no more radical, it's outside. And then we have square root of 5, that is an irrational number, and I'm done with the problem. Feeling okay about that process? Okay, well, practice it. It does take a little practice. Get familiar with that list of perfect squares. That'll make your life a little easier. One of the things I recommend when you take the test, and I put a couple of problems, just do a brain dump of the perfect squares. That way you're not stressing about them. Perfect squares are pretty easy to generate. It's just 1 times 1, 2 times 2, 3 times 3, just going consecutively in the numbers and multiplying them times themselves. That's the perfect square list that you're going to go ahead and use. All right, last little bit is, again, we're just working with radicals, getting comfortable with this because it's maybe part of some of your math future. And so the last thing is, what do I do if I have to add or have to subtract square roots? Okay, well, there's kind of an easy answer and then a little bit of a more complicated answer. The easy answer is this. If you're given 2 roots that are exactly the same, so notice my example here, I'm going to add 9 times the square root of 3 plus 5 times the square root of 3. And the root parts of this are identical. And I spelled identical terribly, and now it's on video. Good job, Perkster. And I'm not using my erasable pens. I'm trying to use out some of the other ones, so I've just messed this up thoroughly. There we go. I put too many syllables because you can't talk and write. I just can't do that. Okay, so these two are identical. When that happens, this is a pretty nice and a relaxing problem. All you're going to do is you're going to add up those coefficients. So I've got 9 of something, and then you give me 5 more. How many total do I have? Yeah, I got 14, and then you don't change the radical at all. Okay, so if you give me 9 oranges and I already have 5 oranges, then I have 15 or 14 oranges. So 14 square root of 3 is the result there. You don't change the radical part at all. Okay. So what I would like you to do is the next problem. It's a subtraction problem, but it's the same sort of thing. This time I am using the erasable pen, so I will not make a mistake. I'm pretty guaranteed of that. Okay, so are the radicals the same this time? Yes, they're identical. So that means, what's 14 minus 20? -6, and it's -6 what's? What am I going to put right after the -6? Square root of 7. Yes, don't change that root at all. It just stays what it is. Fair enough? Okay, so then of course this begs the question, well, that's fine and dandy, but what happens if I have different radicals, like the next problem? So in the next problem, I have 4 times the square root of 50 minus 2 times the square root of 18. These are not the same. Okay, square root of 50, square root of 18 are completely different, so I cannot just say that this is 4 minus 2 times something. That wouldn't work. What you have to do is you have to simplify the radicals first. You're going to use that process that we were just beginning to get familiar with, and we're going to simplify the radicals first. So you're going to help me along on this one, and then you see I got 2 for you to do just to get a little bit more practice as we finish up this section. All right, so first I got 4 square root of 50, so I'm just going to leave the 4 where it is. Not we do anything, but 50. Does 50 have a factor on my perfect square list? Okay, it's 10 times 5. That is indeed true, but is 10 or 5, are either of those numbers on my perfect square list? No. So neither of those are helpful in this situation, but that's a good thing. Now I don't know what, now I know what not to use. What's next? 25 is on the perfect square list. Remember, just take your calculator and just divide out. And so this is going to be 25 times 2. I just want to pause because it's a legitimate mistake to make. Do you understand why we're using 25 and 2 instead of 10 and 5? Okay, that's what matters. Okay, so it's all good. All right, so now I'm going to go over to the other one. And again, I got minus 2 times square root of 18. So I'm going to just leave the 2. Don't really have anything to do with it just yet. And then the square root of 18. Does 18 have a factor that is on the perfect square list? It's 9 times 2. Okay. 9 times 2 is 18. And honestly, that's the hardest parts of the problem. Okay, the rest of this is just some busy work making this look a little prettier. So now the next thing I'm going to do, and by the way, once you've done a few of these and you get used to doing it, I have no problem if you skip this next step. Okay, I'm going to write it so your notes are thorough. Okay, but it's just like anything else. Once you've done it a bunch of times and your brain is used to it, you probably don't need to write this. But I am going to do the product rule of radicals here, and I'm going to give them each their own operator symbol. So I have 4 times the square root of 25 times the square root of 2 minus 2 times the square root of 9 times the square root of 2. All right, now this next step, I'm going to try to do without writing everything down. If I confuse you here, please let me know. I don't want anybody to be bothered by this. What is the square root of 25? It's 5. It's now outside the radical. So what I'm going to do is I'm going to take that 5 and I'm going to multiply it by, what would you guess I'm going to multiply it by? The 4 that's already outside. So square root of 25 you told me is 5 times 4. What's 5 times 4? 20. So these two things right here give me 20 times the square root of 2. Just to make sure you're tracking with that, here's what I want you to do. I want to know, we've got 2 times the square root of 9 times the square root of 2. I want to know it's what times the square root of 2? When you simplify that, what's the number in front of the square root of 2 going to be? Don't shout it out. I want to make sure everybody's tracking with me. All right, now you can shout it out. What's the number in front of the square root of 2? 6. Okay, so I heard enough of you that I don't think I have to ask, but just in case, the square root of 9 is 3. Your calculator will tell you that. Remember, use your calculator. It's a legit tool. I'm not going to tell you can't use it. Okay, so you can use it for the parts of the problem that it works for. So square root of 9 is 3 times the 2 that is already outside the radical. 3 times 2 is 6, square root of 2. And then now I have the identical radical, square root of 2. So 20 minus 6 is 14, square root of 2. All right, so what I would like you to do, please, is exercise 8. The nice thing about exercise 8 is there's only one of the radicals you have to simplify. Okay, so I just wanted you to do a slightly simpler version. And then exercise 9, when we get there, you don't have to do it yet. Exercise 9 is like the problem that I just did, example 5. Okay, one at a time. right, so when I go to engage with this problem, the first number I see is the square root of 3. Can I simplify square root of 3 at all? No. Quick quiz from a previous unit. 3 is what kind of number? Prime, yes, it's a prime number. It's the only factors are 3 and 1, so it's called a prime number. Okay, so square root of 3 is going to stay square root of 3, nothing to do with that. But 12, I can simplify. What is the factor from the perfect square list that's part of 12? It's 4 times 3. Yes, fantastic. Now here's the step that you can skip if you're getting good at this, but I'm going to write out that I'm going to give them each their own operator symbol. That's the product rule of roots or the product rule of radicals. But if at some point you're capable of just saying, oh, square root of 4 is 2, and you bring it outside the radical, that's great. You're just making the process a little quicker. So then I got the square root of 3 plus the square root of 4 is 2 square root of 3. And the reason I gave this problem, in addition to giving us opportunity to practice that, is what's the number in front of the square root of 3, even though it's not there? A 1. A 1 is implied. Okay, it's kind of like a variable. If you did take any sort of algebra class in high school or somewhere, there's a 1 here, even though you can't see it. And then 1 plus 2 is 3 square root of 3. All right, last problem from this section. This is very much like example 5 that we just did, so I'll leave it on the screen for you to see and follow along with, but give exercise 9 a try. All right, so I'm going to get started on this. If you got any questions, ask it. This is the last problem from this section. So we've already simplified the square root of 12. We just did it in the previous problem. So this is 5, and then the perfect square factor of 12, that is 4 times 3 plus 2. What's the perfect square factor of 27? Okay, it's 9 times 3. I can hear more voices, so it sounds like you're getting a little better at using that list. That's great. Okay, anything you do repeatedly, you're going to get better at, no doubt. All right, so I'm going to use the product rule here, and so I'm going to give 4 and 3 each their own operator symbol. So square root of 4 times the square root of 3, and then plus 2, and then again, product rule. So square root of 9 and times square root of 3. All right, so here we go. What's the number in front of this first square root of 3? Okay, and then what am I going to, you said 2, what am I going to do with that 2? I'm going to multiply it by the 5 that's already there. So what's 5 times 2? That is 10. Everybody with me? Anybody not see where that I think once it clicks, that's not a hard step to make, but I understand getting there can take a little time. We okay? All right, plus then what's the number in front of the second square root of 3? Okay, square root of 9 is 3 times the 2 that's already there is 6. Great. And now I have 10 square root of 3 plus 6 square root of 3. They are identical radicals, and so I can combine them. By the way, if you encounter a problem, let me just pause for a moment. If you encounter a problem that's like 5 square root of 2 plus 7 square root of 3, you can't do anything. Okay, I don't think there are anything like that in the homework, but just in case, if the radicals are different, you're done. Okay, you can't go any further. You're just going to stop right there. But this one's not that. 10 square root of 3 plus 6 square root of 3. The 10 plus the 6 is 16, and then we keep the square root of 3. We don't change that one bit.